Hello, everyone, and welcome back. I'm going to take this video today to give you a very brief introduction to a field of philosophy referred to as the philosophy of science. Now, introducing this concept might sound a little strange, right? Especially because a lot of you are entering into STEM majors or maybe want to have STEM majors. And so might sound a little weird that philosophy has a branch that studies science. But the first demarcator that I want to draw is that when we talk about the philosophy of science, and when we're approaching scientific disciplines from a philosophical perspective, we're not so much interested in the scientific content of those disciplines, but rather we're interested in the philosophical questions that arises from those disciplines, if that makes sense. So if you take something like biology, right, and if you were to take a philosophy of biology class, which is a very specialized class, it would be different from a general intro to biology where you might examine something like the structure and functions of different parts of the cells. I'm sure you have to take like a test on that. It would not so much be like microbiology where you had to label all the different parts of the cells. It would more so be asking general questions that arise out of the philosophy of biology. Questions like, what is the meaning and purpose of function or teleology within biology? And does this point to or answer any other philosophical questions? If you're interested in what that would sort of look like, I have an interview on my channel with a philosopher named Seth Hart, who specializes in the philosophy of biology, if you want to get a sense of what that means. So the philosophy of science, very broadly speaking, is interested in these philosophical questions of metaphysics, epistemology, ethics that arise out of particular scientific disciplines. And the philosophy of science is sort of the big general category, and underneath that big broad umbrella, we have very specific departments of the philosophy of science: the philosophy of biology, the philosophy of physics, the history of science, and the philosophy of science also have a very close relationship to one another. Now, although I said that the philosophy of science is a relatively new field, really getting its start post World War II in the 1940s, 1950s. That's not to say that no one was doing the philosophy of science prior to the 1950s. Of course they were. And to briefly give a very broad overview of the history of the philosophy of science, we can kind of divide it up into these three stages: pre-modern, modern, and 20th century. Pre-modern philosophy of science includes a lot of the people that we have already talked about. If you look over the history of philosophy, that can include the pre-Socratic philosophers. It could include early Chinese philosophers like Confucius and the people surrounding Confucius. It could include early Indian philosophers, early African philosophers. Anybody who was interested in the broad term cosmology, what the universe is like and how the universe is formed and structured, we could say would fall into the philosophy of science. But we make this separation between pre-modern and modern because it's really with modernity, beginning in the 15th and 16th century, that modern science comes into being. And if you watch my, sorry, ambulance is going by. If you watch my video on the Enlightenment, you'll kind of understand historically why that is, because it's with one of the characteristics of the modern period is the rise and the development of modern science, of contemporary science, science as we know it. And that, of course, radically changes the philosophy of science. So pre-modern philosophers, if you look at like the pre-Socratics, they were largely interested in questions about like where the world came from, where human beings came from, human beings' place within the natural structure. You see these sort of questions being asked on the other side of the globe by Chinese philosophers, Chinese Taoist philosophers. What is the role and nature of human beings within nature at large? Those sorts of things. Modern philosophy of science will largely be interested in what we would call like the scientific method. How does science do what it do what it does? Why is science so successful? Why has science been so successful historically speaking? So early modern philosophers of science like Rene Descartes, for example, were interested in exploring and understanding what exactly the scientific method is and how it operates. And that's still a question that philosophers of science are kind of wrestling with, because there hasn't really been a great answer to that. And it's not super clear what exactly science is, but we'll get into a little bit more of that later. And in the 20th century, we saw another kind of shift in the academic study of the philosophy of science. And this was largely a result of academic specialization. So the word scientist didn't really exist prior to the 19th century. They were just called natural philosophers, and a natural philosopher was just anybody who studied any aspect of the natural world. And this was the era of like great polymaths, people who were really good at mathematics, but who were also writing like treatises on government, right? So if you take a philosopher like John Locke, who's writing books about human psychology while at the same time writing books about natural right theories of government, they're kind of interested in all these different areas, and they were able to do that because specialization hadn't occurred yet. And specialization just means what it sounds like it means. Specializations related to the rise of the public school system, and with the rise of the public school system, you have more focused areas of studies that emerge out of that. And this is what the modern university and even the modern high school system is based off of. The longer you're in school, the more specialized you become on one specific area. Right, this is what college majors are. You choose to major in biology, and you start off with the general study of biology, and then you get into environmental biology, and then your next class is about the environments of specific mammals, and then from studying mammals you start to study rats. Right, it gets more and more narrow, and that's what I mean by specialization. Some people call it hyper specialization, but the 20th century changed all of that, and with that change came a change in philosophy, especially after the Second World War. The biggest movement in the 20th century history of the philosophy of science was the rise of the logical positivist, the Vienna Circle. These were people who were greatly interested in statements of epistemology, right? What makes something true, or how do we know what we know? And they were interested in scientific epistemology and how and why scientific epistemology differs from other sorts of epistemology, such as like religious epistemology, right? And why is it that scientific claims about the world, about reality, why is it that they seem to be more solid than other claims, other sorts of claims about reality? Why does science seem to have this special place when it comes to knowledge about the world? And so they were interested in figuring that out. One of the things that they developed was the verification principle of meaning. I don't really have to go into all of this. It's kind of more historical stuff. But just to tell you what some of the big movements were. So the logical positives kind of fell out of favor. And then you get the kind of the big four in the history of science. If you're interested in pursuing philosophy, or if you're just interested in the philosophy of science, period, the four major philosophers of the 20th century philosophy of science, Karl Popper, Thomas Kuhn, Irene Lactoses, and Feyerabend. I can't remember, Paul Feyerabend. this is for the most important people, and I can't remember their names, right? Those are the biggies. We're going to focus on kind of the central questions that arose out of 20th and 21st century philosophy of science. But very briefly, that's just kind of a general history there. You the pre-modern to the modern period and to the 20th century period. So one of the big questions to arise out of the 20th century philosophy of science is what's called the problem of demarcation. The problem of demarcation. Very simply put, this refers, it's a problem that refers to how do you separate or how do you distinguish, on the one hand, real science from, on the other hand, pseudoscience? How do we tell those two apart? How do we separate, distinguish real science from pseudoscience? So, for example, nowadays, right, one of the biggest debates in and surrounding science is, of course, surrounding health science and the use and the mandating of the vaccine. And so there's a lot of people arguing and debating about what vaccines are, whether or not vaccines are safe, whether or not the government should be able to force people to get vaccines. And there's this entire group of people now, this anti-vaccine, the anti-vax movement has been around since like the early 90s, right? But it's come into the spotlight again when COVID vaccines were being pushed out. But what makes anti-vax science differ from regular, modern, established medical science? What's the difference between the two? That's the problem of demarcation. The demarcation gets its start with the philosopher Karl Popper. In Popper's day, there was a different sort of scientific controversy going on. The two big schools of thought that were accepted in Popper's day as science, that he did not believe was science, were Marxism and early 20th century psychoanalytic theory. People like Freud, Jung, that sort of thing. So there was a lot of people in the mid 20th century. This is after World War II. It's the height of the Cold War, and so there was this kind of battle between East and West, between capitalism and Marxism, and there were a lot of philosophers who were interested in studying Karl Marx, and there were a lot of these philosophers saying that Marxist political theory was quote unquote scientific. And so Popper asked the question, well, what's the difference between Marxist theory and Einstein's theory of general relativity? What characteristics separate those two things? Or Freud's psychoanalytic theory and the behavioral psychology of the mid 20th century? What's the difference? And what Popper will do is he'll start to come up with criteria that Einstein and B.F. Skinner was the behavioralist, right? I might get that wrong. He'll come up with certain criteria that Einstein and Skinner meet that that Marx and Freud don't meet. And this was one of the first answers to the demarcation problem. And it's known as Popper's principle of falsifiability. Falsifiability, to use Popper's own words here, this is Popper, by the way, later on in life. Falsifiability, Popper will say, are statements or systems of statements in order to be ranked as scientific must be capable of conflicting with possible or conceivable observations. Statements are systems of statements in order to be considered scientific must be capable of conflicting. This is what it hinges on. Must be capable of conflicting with possible or conceivable observations. Put in a different way, scientific statements about the world are statements which are demonstrably true or false. Or scientific statements about the world are statements which can be proven false. They can be falsified. And if these statements are falsified, then they're not truthful. Okay. So going back to what's the difference between a Marxian interpretation of history and politics and Einstein's theory of relativity. He's not interested in the content of those two things for the purposes of this conversation, right? What he's interested in is what kind of statements these two systems make. And one of the things that he says about Marx, that he also says about Freud, that with Marx, you can look back, a Marxian can look back at all of human history and frame it in terms of the struggle between the rich and the poor. Doesn't matter what it is. You can look at the Neolithic Revolution, 10,000 BCE. You can look at the rise of the Sumerian civilization. You can look at the rise of the Ming Dynasty in China. You can look at the American Revolution, the French Revolution. All of human history can be explained in terms of economic conflict. And so the Marxian is always right in his or her interpretation of history. And that might sound like that's a good thing, right? That your theory can explain everything. But for Popper, it's not. For Popper, those statements, there needs to be what qualifies something as scientific is that it's falsifiable. And so he contrasts a Marxian view of history with Einstein's theory of relativity. So I love the history of early 20th century physics, but I'll try to limit it for this video. So Einstein comes up with his general theory of relativity, 1905, 1906, I can't remember the exact date. He publishes his famous paper on the electrodynamics of moving bodies. And it causes a really big stir in the scientific community because a lot of the claims that Einstein was making in that paper kind of bumped up against the established physics of the time, especially the claims that he was making about the status of the speed of light within physics, and likewise about the synchronicity of observers observing a particular event. The conclusion of Einstein's paper famously said that observer A and observer B can observe the same event at different times because of the speed of light. He uses the example of moving trains. I'll make a separate video about that to explain that a little bit more. But the conclusions that he came to were, up until that point, unestablished and went against the established consensus at the time. Now, this caused a stir, but Einstein was able to provide mathematical justification for his claims. But his claims in 1905 weren't experimentally verified yet. So there was a time period where people were discussing a lot of Einstein's ideas. They didn't know if it was an accurate depiction of reality or if it was just a good mathematical description or maybe even a useful mathematical description. That changed when Arthur Eddington observed the bending of light during a solar eclipse, which experimentally, empirically validated a lot of Einstein's claims. And it was that empirical validation that lent credence to the rest of Einstein's claims, which would later be empirically verified. So what Popper says is what makes relativity successful, what makes relativity a good explanation about reality, is that Einstein could have been proven wrong. If Eddington did not observe the bending of light, Einstein's theory would not be perceived as empirically credible and most likely would have fallen out of favor. So that's what he means by falsifiability, that scientific claims can be proven wrong, that in order for something to be considered scientific, there has to be situations that we can set up to prove that thing incorrect or to have good reason to believe that it's not correct. Popper's idea of falsifiability in the history of science has been hugely influential. It's still one of the main ideas used to answer the problem of demarcation. Now, there were some problems with it. The problems with it largely come from the philosopher Thomas Kuhn that I mentioned before. One of the big problems with Popper's idea of falsifiability, according to Kuhn, is that it didn't really match well with what we know from the history of science. That this idea of falsifiability might be a philosophically sound idea, but that if you look at the way that scientists actually do science, falsifiability plays a very minor, insignificant role in how science develops. We'll dig a little bit more into this in a second. But as a result of Kuhn's criticism, this problem of demarcation became kind of the hot topic of the day, and two other major philosophers will give their own responses to it. Lactoses' answer to the problem of demarcation was that successful scientific theories were those which developed research programs. This is what Lactose says. A given fact is explained scientifically only if a new fact is predicted with it. The idea of growth and the concept of empirical character are soldered into one. So Lactose's idea here is that a scientific theory will produce more questions that need to be answered, and in producing more questions that need to be answered will produce a bigger and wider body of knowledge / research. The example that Lactose gives is the difference between astronomy and astrology, right? So astronomy, you could take an astronomy class at whatever school you're at now. Astronomy is the study of celestial bodies. You investigate the movements of planets around stars. You investigate star formation, galaxy formation. You talk about things like the Big Bang Theory and how galaxies are moving apart from one another. Most of that, well, all of that, not most, all of that falls well within the realms of science. Versus you think about something like astrology. This is horoscopes. This is the belief that the locations of the planets in the sky at the time of your birth have some sort of influence on your personality. Both of these disciplines, now, if you look at it just like on a surface level view, you might want to immediately dismiss astrology because of the certain preconceptions that you might have about it. But Lactose says, like, listen, astrology uses as complicated of mathematical calculations as astronomy. Using astronomy, you can actually predict, and ancient peoples did. If you look at ancient Egypt, if you look at the ancient Mayans, a whole host of ancient civilizations were very accurately able to predict the motions of the planets and the motions of the moon in the night sky. Using astronomy, they had religious beliefs about these movements. So Lactose says, well, what's the difference then? Why is astronomy considered a science, but astrology is not? His answer is that because astronomy, modern astronomy, started by Nicholas Copernicus, it produces more questions that have to be answered. And as a result, it changes and grows over time. So modern astronomy, starting with Copernicus arguing for a heliocentric model of the universe, well, that raises the question, well, okay, if we accept that the planets are orbiting around the sun, why are they? Right? Copernicus didn't really have an answer for that. He could just tell you that they were and how to locate them in their orbits around the sun. Kepler comes along and says, well, the orbits of the planet seem to be a little off. They're not orbiting around the sun in perfect circles, that it's more like an oval type shape. Newton was the one that finally was able to give a mathematical answer to this question, that it was because of the impact of the sun's gravity, that it was the gravitational pull of the sun that was causing the planets to orbit around it. And so you have new answers, but these new answers always produce new questions, and these new questions help us to understand, to go back and understand those original questions. Astrology doesn't do that. In fact, astrology has basically remained the same for thousands of years, right? So Lactose, it's a more pragmatic approach. He says, hey, listen, if you want to know whether or not something is a scientific discipline or not, you look at whether or not it has produced successful research programs. And then Paul Feyerabend comes along. Feyerabend is just kind of comes along and breaks everything up. Feyerabend says, listen, none of these responses, Popper's, Kuhn's, or Lacatose's response, that with all of their responses, you could think of examples in which this doesn't apply. Disciplines that you want to consider scientific, that you can no longer consider scientific. So Feyerabend, in his book, Discord Against Method, says that there is no demarcation, that it's impossible to separate science from pseudoscience. He says, quote, science is essentially an anachronistic, anarchic, there we go. Science is essentially an anarchic enterprise. Theoretical anarchism is more humanitarian and more likely to encourage progress than its law and order alternatives. Feyerabend basically says that there is no established demarcative method, there is no established scientific method, but that this doesn't stop science from doing its thing, that it's going to continue to do what it does with technological progression and scientific progression, and that basically it doesn't need to answer these questions of philosophy. Right. All right, so that's the problem of demarcation. The next big question facing the general philosophy of science is this question of scientific progress. Is science the arbiter of truth, capital T truth, right? Does science lead us to truth? Can science tell us what the truth is? And is scientific knowledge progressive? Do we know more about the world today than ancient people did? Most people's immediate response to that is, well, yeah, of course we know more about the world today than ancient peoples did, right? We have all this wonderful technology at our disposal. We have like GPS, we have cell phones. I'm delivering this to you all across the internet right now. Ancient people, no matter how technologically advanced they were, couldn't even dream of this being a possibility, right? Well, Kuhn kind of presents some historical challenges to those traditional assumptions. Specifically, Kuhn's view of the history of science is going to challenge this idea of scientific truth. Kuhn's going to point out that, well, I'll just jump straight into it. So, according to Kuhn, there are different stages of scientific development. These are different historical stages. He's going to use this word paradigm here. Kuhn was the first to kind of introduce paradigm into the jargon of the philosophy of science. But Kuhn says that the history of science is the history of the change of one scientific paradigm to the next scientific paradigm. And that the history of science can be viewed in these different stages. The first stage is the pre-paradigm stage. The second stage is normal science. The third is crisis/paradigm shift. The fourth is post-revolution, after the scientific revolution, and the establishment of a new paradigm. And most of Kuhn's book, The Structure of Scientific Revolutions, is largely historically based, uses a lot of history to support and to build off of these points. So Kuhn says that all science starts off in a pre-paradigmatic stage. Take your pick. So look at the history of biology, for example. Modern biological theories don't really develop until the 19th century, believe it or not, with Lamarck's idea of biological evolution. And then, of course, Darwin's idea of biological evolution. But if you look at biology prior to the 19th century, there were several different ideas about where species came from and what separates one species from another species. There were ideas that invoked divine creation, the spheres of creation model. Some people did support a kind of evolutionary model. Most people supported a creative model in which God creates present species in their current condition. But nobody really had kind of knockdown, drag out arguments to convince the other side. And this is what Kuhn calls a pre-paradigmatic stage. Or if you look at astronomy prior to the 16th century, right? You had different models of the universe. You had an Aristotelian model, kind of what's called the two-sphere model, that you had the heavenly sphere and the earthly sphere. You had the Ptolemaic model and Ptolemaic calculations that could help you identify and organize the location of planets in the night sky. But no one really had a good concrete answer to some of these fundamental characteristics, like why planets move in the night sky in the first place, and whether or not the Earth moved. That's pre-paradigm science. That's the first stage. The second stage is where you have the introduction, acceptance, and establishment of a scientific paradigm. So let's stick with astronomy. So you have the pre-paradigmatic astronomy prior to the 15th century. Copernicus comes along and introduces a heliocentric model, a sun-centered model, that you have the sun in the center of our solar system, and then you have the other planets rotating around that central sun. And this paradigm, this scientific theory, helped to answer and establish a whole host of questions that up until that point had not been answered. So that's the second stage of scientific development. And Kuhn calls that second stage normal science. And normal science is characteristic of what we think of when we think of science nowadays. Normal science is the science that you're being taught in school right now. Normal science, if you go into a scientific field, these are the ideas that you have to accept. And Kuhn calls he's been criticized a lot for his views about science, but he says that normal science, for the most part, is just equivalent to like puzzle solving. He says, under normal conditions, the research scientist is not an innovator, but a solver of puzzles. And the puzzles upon which he concentrates are just those which he believes can be both stated and solved with the existing scientific tradition. All right, what the heck does that mean? Well, let's go back to Popper for a second, right? Popper said that what separates science from non-science is falsifiability, that scientific claims are able to be proved wrong. Kuhn says that in the second stage in normal science, that no one's really attempting to falsify these claims because they're just established, they're just accepted. So let's go back to the example of vaccine science. Kuhn says that the person going through medical school right now is taught how and why vaccines work. And any research that they might do, researching vaccines and studying vaccines is not falsifiable, right? They're not setting out to debunk vaccines. That system of thought is just accepted and then put into practice by people on the front lines giving the vaccines, if that makes sense. To use a less controversial example, that one, a lot of stuff going on right now. Evolutionary biology, right? If you're a biology major, evolutionary biology, Darwinian biology is the established paradigm of the day. Why is the established paradigm for the day? Because it has an overwhelming amount of support for it. The same with vaccine science. All of the established evidence points towards it being true. And so that's what you're taught. And the evolutionary research biologist who's researching, I don't know, changes in cellular biology. You could tell my ignorance of biology here, right? But the evolutionary research biologist who's maybe studying how microorganisms change, maybe to prevent a new vaccine or something along those lines, is not setting out to falsify the claims of microbiology. The opposite of that is true. So the pre-paradigmatic stage leads to the establishment of normal science. Eventually, says Kuhn, within that realm of normal science, there will start to be areas that start to present us with some conceptual theoretical challenges that aren't able to be answered by that current scientific paradigm. Physics is going through this now. Right, so the big theories of physics of the 20th century, relativity and quantum physics, microphysics, quantum mechanics. We're not super sure how those two relate or if they relate to each other, but the rise of quantum mechanics was brought about by questions that Einstein's theory of relativity didn't really seem to have a good answer for, specifically the mechanics of how these microparticles move and interact with each other. And there seemed to be parts of relativity that kind of broke down at certain levels, right? So relativity, for example, could point us to the conclusion of something like a Big Bang, the singularity happening, but relativity can't explain what a singularity is. But quantum mechanics might be able to explain that for us. So there are certain fundamental problems that arise out of normal science that the paradigm cannot answer. And this leads into the next stage of the crisis of the paradigm, a competition to see who can answer that question, and then a paradigm shift. An example of a paradigm shift happening with, for example, the transition from Newtonian physics to Einsteinian relativity. There are certain questions that Newtonian physics could not answer. There were major problems that started to become evident in the 18th and 19th century. For example, why planets like Mercury seem to have a regular orbit. Newtonian mechanics couldn't explain that. And it was as a result of this that you have the development of like non-Euclidean geometry being kind of the bedrock and the basis for relativity theory. But the problem, going back to this question of, well, are scientific theories true? You might accept that historical development I just told you, but what does that mean for truth? So prior to the 20th century, we would have said that Newtonian mechanics is true. It's true because it describes the natural world in a very successful way. Well, what about post-Einstein? Is what Newton said still true? On the one hand, we want to say, well, yes, it's still true because, right, you could still, you're still taught Newtonian mechanics. Newtonian mechanics is still useful in certain areas. But on the other hand, it's not as true anymore because there are some things that Newtonian mechanics can't answer that Einsteinian relativity can. So was Newton's physics true at one point of time, but not true anymore? Or was it kind of true at one point in time, but now it's less true? This is where it starts to become problematic. Not to say that philosophers haven't attempted to provide answers for this, but this is the big issue. Right. All right. Well, I have rambled on for long enough. If you have any questions about any of this stuff, let me know. If not, have a good one, and I will see you next time.